Hello and welcome to the TTI Distribution Download, the podcast where we talk about all things happening in the world of electronic components with the specialists of TTI.
Thanks, Jim, and hey, everybody. Thanks again for tuning in to the TTI Distribution Download. I'm Steve Prohosky. I'm a business development manager at TTI. I've got over 30 years of experience in the electronics industry, 4 of which are here at TTI. I'm joined again by Pat Denton, our TTI Technical Marketing Director, and Pete Pytlik, who's a Senior Manager, North American Field Application Engineering at Littelfuse. Littelfuse is one of our premier partners in the area of circuit protection, so we're very fortunate to have Pete and his expertise joining us today.
Thanks, Steve. And again, I'm Pat Denton, Director of Technical Marketing here at TTI, and thanks for joining us, Pete. We appreciate it. Last time we talked a little bit about electrostatic discharge, or ESD. What causes ESD?
Great question. So ESD is caused mainly by a transfer of charge between 2 dissimilar materials. One of the easiest examples I think that everyone can relate to is when you walk across a carpet and then you touch, let's say, a doorknob, and you see that, and you may see or you may actually also feel that discharge. And that discharge can actually be several thousands of volts or tens of thousands of volts. And that will actually depend upon the materials, the area of contact, environmental conditions, what that static discharge level will be. Again, generally it's in the thousands of volts. So again, probably one of the most easy examples, again, walking across the carpet. I think everyone's done that and probably had an electrostatic discharge at one point or the other. So there is a buildup of charge, and it is important to protect against.
That leads right into my next question. And now that we understand a little bit more about it, do we need to protect against ESD?
Yes, definitely. So as I mentioned, when that charge is transferred, built up, it can be in tens of thousands of volts. So now, if that gets discharged into an application, it could be a general electronic type application, it may be a computer port, that level of ESD can very easily damage the sensitive electronics. So again, it is very important to protect against ESD, and we do have different technologies that offer protection against ESD.
So it's the small components that we're trying to protect against here with ESD. And going back to the compliance and standards, what are the different types of standards that regulate ESD protection?
Sure. So there's actually several standards. There's device standards, and then there's also end product standards. A lot of times that will be one and the same. So let's take a look at a couple of those standards. And just as with overcurrent, overvoltage, the first thing that a designer needs to do is look at the standard and which level do they need to protect against for their particular application. So the most common ESD standard, which is a end product standard, is IEC 61000-4-2. This defines both the contact discharge and also air discharge magnitude of the ESD. There are also other types of ESD standards. The other one is a human body model. That standard is basically used for the manufacturing stage. So that is really the minimum amount of protection that a device or product needs to withstand. Some of the other ESD standards are for automotive. These are ISO standards that define what the ESD event will be both inside the vehicle and outside the vehicle. Some of these standards are very similar in magnitude of the ESD threat. Generally, we do need to protect against more than just the human body model. Again, this is where an application needs to have the limited amount of protection, or smallest amount of protection really coming out of the manufacturing environment. So what our devices will do, it will protect against, we'll say, the next level, okay, the end product standard, to make sure that we're protecting the electronics.
Well, once again, happy to have experts like you with us to help us walk through the standards that are out there. So thanks for that. I'm thinking about all the different electronics that are now present in cars and vehicles these days. Are there any different standards for the automotive industry versus, say, general electronics or industrial applications?
Yes, there are. So there are application-specific standards for the automotive environment for ESD. So that standard is an ISO standard. As I mentioned previously, it will define what that ESD thread environment is, both for interior applications, meaning cabin, and then also external applications, meaning outside the vehicle. So again, that ISO standard will define what that threat level magnitude is. And then based on that, the designer will need to select the appropriate ESD suppressor to protect against that threat.
And with all the different technologies available, which technologies are best for ESD protection?
So basically, there's 3 technologies for protecting against ESD. The first one is MLVs, otherwise known as multi-layer varistors. The second is polymer-type devices. And the third are silicon-based devices. There is a reason why a designer would select one over the other. The first is, what level of ESD do they need to protect against? The second is the clamp level. Again, as we mentioned in our previous episode on overvoltage, when there is an overvoltage or ESD event, again, ESD is on a much shorter time scale, so we kind of give it its own separate category. We're talking about nanoseconds for ESD versus microseconds or longer for overvoltage. So regardless of overvoltage or ESD, we're going to have a voltage that could be in the thousands of volts. Again, that will present itself onto the electronics. So we want to clamp that voltage to below the damage threshold of the components, electronics we're trying to protect. So depending on the application, okay, if it's a high-speed application, we're looking to select a device. In many cases, there will be a silicon-type device to protect against ESD, very high magnitude, clamp that voltage as low as possible. Silicon versus the other technologies will have the lowest clamping voltage, and that's because they will generally have the lowest dynamic resistance. The other 2 devices, mainly for general-type applications. So multi-layer varistors, a lot of times if we're looking to protect against push buttons or maybe DC inputs, where high speed is not really of a concern. We don't need to have that very low capacitance. So MLVs will typically be used in those applications. Polymer devices, generally for mobile antenna applications, the lowest capacitance of the 3 devices. Now we're looking at below 100 femtofarads, 0.1 picofarads. So that's depending on the application, whether it's a port, general type application, maybe push button, what the magnitude is, what the application is really going to determine then which suppressor will be selected.
Is there a cost versus performance ratio or a derivative or a consideration you have to use when you apply the different technologies or materials?
Sure, but it really comes down to, is the application going to be adequately protected? So just to give you a specific example, if we look at a common port type, it may be USB, and we see that the data rates are significantly increasing. It may be HDMI. As those data rates have increased, the complexity of the chips has gone up significantly. The feature sizes have gotten much smaller. Designers of the chips are actually putting less ESD protection on board the chip in order to incorporate other functions. So those chips are generally very sensitive to ESD in the end application. So really we're looking to use the best possible ESD protection device. And again, for those types of applications, generally, it'll be silicon. In some cases, you may be able to use a polymer type device. But it really comes down to offering the best protection, making sure that those electronics are protected.
Is it fair to say the silicon-based ones are the most expensive, or is that not necessarily the case?
Not necessarily the case, but depending on the level of protection, packages, they may be, versus the other technologies. But again, in some applications, you can use any one of the 3, but you really need to the designer really needs to look at that application, how susceptible it is to ESD, and then appropriately select the correct suppressor.
And you mentioned a port application. So behind that port, whether it be a USB or HDMI port, is your devices sit right behind that connector on the printed circuit board on each circuit? How would you describe where it's used in the application?
That is an excellent question. Placement of ESD suppression devices. Generally, where you want to place the device is as close as possible to the thread entry point. So in most cases, they'll be right at the connector. The reason for that is we want to reduce or bring down that voltage as soon as possible, and then use the rest of that trace impedance to our benefit and bring that voltage down even further. So first, place the ESD suppressor as close as possible to the entry point. Again, there'll generally be a connector. And then also as close as possible to the trace itself. ESD suppressors are placed in parallel. The reason for placing it as close as possible to the trace is when that ESD event presents itself onto the circuit, what will happen is the ESD suppressor will turn on. When it turns on, you're going to have a certain amount of now current flow through the device. And that's actually how we bring down that current. The current flow through the dynamic resistance of the suppressor is really what determines what that clamp level will be. Well, if I have a ESD suppressor and it is located, we'll say a particular distance or some distance away from the trace itself, what will happen is that trace itself will also have an inductance. So if I have a current going through an inductance in addition to the ESD suppressor, those voltages will add. So again, very important when it comes to ESD placement, as close as possible to the connector, and then also the ESD suppressor as close as possible to the trace itself.
Going back to the technologies, can you expand on the construction and characteristics of those technologies?
Sure. So looking at MLVs, the first technology, multi-layer varistors, very similar to metal oxide, but a little bit of a different configuration, layered configuration. Really what we're trying to do there is to get as much possible energy handling capability and also to some extent reduction of capacitance. Similar technology, a little bit different construction. Multi-layer varistor versus a metal oxide varistor, which would be used for larger overvoltage type protection devices. The second type of device is a polymer type device. And with polymer devices, it is basically a polymer matrix with different conducting and semiconducting particles. So when that ESD event turns on the polymer device, basically you're going to have conduction through those metal and semiconductor particles. And then that's really what's going to bring down that voltage. Third, silicon type devices, similar to other types of transient voltage suppressors, PN junctions, but again, specifically tailored for ESD events. Low capacitance. The structures are also so designed to be able to handle the ESD energy. So there are differences between the three different technologies. And again, what we're trying to protect against is ESD, a certain magnitude, bringing it down, that voltage below the damage threshold of the electronics we're trying to protect.
It's been really great having you here, and thank you for being with us in this circuit protection series. And one final question. When selecting devices for a circuit, can you walk us through the steps for selecting ESD technology for a circuit design?
So what the designer first really needs to do is take a look at the standard and the level they need to protect against. So just use an example. It may be the worst case, okay, at a particular standard. So this would be the highest voltage, highest duration, pulse width. And then what the designer needs to do is look at, is that device going to meet that standard? Second is, how sensitive are the electronics? Okay, and what clamp level is required? I'll also mention third is this a high-speed port or low-speed port? So we do need to be mindful because faster speed ports, faster data rates will require a lower capacitance part. So look, what is that threat magnitude, ESD level? Also, is it a contact? Is it an air discharge type of event? Second is the ESD suppressor, the technology that was selected, being able to actually handle that ESD pulse. And then third, is it going to protect against that end application, meaning that are we going to have that clamp voltage that is required?
So happy to have experts like you available for when the circuit design portion comes in.
Thanks, Pat, and thank you, Pete, for your time today and for your insight on ESD. Listeners, if you're just joining us today for the first time, be sure to listen to our other great episodes with Littelfuse on overcurrent and overvoltage. These podcasts are available wherever you get your podcast and on tti.com/podcasts. Thank you again for your time today, gentlemen, and thank you, listeners, for listening.
That's it for this episode of the TTI Distribution Download. For more information on any of the topics you heard about today, reach out to your nearby TTI branch at 1-800-CALL-TTI or visit us online at tti.com.